moving along to example 4. So now things are going to start getting more abstract, more conceptual. This is where you really need to understand what's going on, and if you don't, you've got to come into tutorial and or after school to get help. Okay, recall that the answer to an inverse trig problem is an angle. Sine inverse of rad 3 over 2 is some angle alpha. Cosine inverse of 1 is some angle beta. Okay? Now these ones are easy to do because these are special values from the unit circle. So it's a little easier to do this one. You think about the unit circle. You think about what angle would make sine equal to rad 3 over 2. And that angle is pi over 3. Then you think about a different angle that makes cosine equal to 1, positive 1, and that angle in the restricted range is 0. The other time is 2 pi, but that's outside of the range, so we use 0. So this is equal to sine of pi over 3, and sine of pi over 3 is rad 3 over 2. So rad 3 over 2 is the answer to this. Now, again, you can check this on your calculator. Just make sure, actually it doesn't really matter what mode you're in this case because, yeah, it doesn't matter. I'm in radian mode and that's fine. So I will do sine of the inverse sine of rad 3 over 2 plus the inverse cosine of 1. And there's the decimal that I get, and then I'm going to check that with rad 3 over 2. And they are, in fact, the same decimal. So I know that I did this correctly. Okay. B and C are going to be much trickier because these are not special values from the unit circle, yet you are still being asked to find the exact value. That means no decimals, and that translates to no calculator. Okay, so this is where you have to recall. This is an angle, and so is cosine inverse. Tan inverse of something is an angle, cosine inverse of something is an angle. So this is actually a sum identity for cosine. Because it's cosine alpha plus beta, where alpha is the inverse tan of 4/3, which is an angle, and beta is the inverse cosine of 12/13, which is also an angle. So I'm going to use the formula for the sum of cosines, and that is cosine alpha cosine beta minus sine alpha sine beta. Okay, so I have cosine of inverse tan of 4/3 times the cosine of cosine inverse of 12/13 minus sine of tan inverse of 4/3 times sine of cosine inverse of 12/13. So that's, I have cosine alpha cosine beta minus sine alpha sine beta. Okay. So this one right here is really easy. The cosine and the cosine inverse cancel out. So this one is 12 over 13. This is the one that'll be harder, minus these two are harder. So actually what might be easier is to draw a picture for angle alpha and angle beta. So these are both positive, which tell me that these are both in quadrant 1. So here's angle alpha. And tangent is opposite over adjacent, so this would be 4 over 3, and so I can use Pythagorean theorem to find the hypotenuse, which would be 5. So this right here is basically just cosine of alpha, and this is sine alpha. So cosine of alpha is 3/5, so this whole thing is 3/5. Sine of alpha is 4/5, so this whole thing is 4/5. And then cosine of beta, we already figured out, is 12/13. I just need to figure out sine of beta, because this is beta. This is beta. So we draw the beta triangle. The beta triangle is also in quad 1 since 12/13 is positive. Cosine is adjacent over hypotenuse, so this would be 12 and this would be 13. So using Pythagorean theorem, I can find that this side would be 5. So cosine of beta, as we already figured out, is 12/13. Sine of beta is 5/13. And then I just simplify from there. So then I get 3 times 12. These are being multiplied together. So 3 times 12 is 36 over 5 times 13, which is 65, minus 20 over 65. So the final answer in exact form would be 16 over 65. And you can check that solution on your calculator as well, the same way that I had checked my solution for A. So let's just do it really quick. So it's cosine of tangent of cosine of the inverse tangent of 4/3 plus cosine inverse of 12/13. And I get that fraction, and then, or that decimal, sorry, and then I will divide 16 by 65, and I get the same decimal. So that's what tells me that this is the correct answer. Okay. Then for the last one, I ran out of room. So first I'll start it on this side, then I'll finish it on the back. So again, we have to recall that this quantity is an angle, we'll call it alpha. And this quantity is a different angle, we'll call it beta. And I'm basically taking cosine of alpha plus beta. It's adding two angles inside a cosine function. So I'll go ahead and use that same identity that I used in part B, cosine alpha cosine beta minus sine alpha sine beta. And what I will do is I'll draw a triangle for alpha, and this is going to be in quad 1 because 2/3 is positive. And then I'll draw a different triangle for beta. This will be in quad 4 because the value is negative, and tan inverse is restricted to quads 1 and 4, and so I will use quad 4. And I will do this on the back. So for my alpha triangle, which is in quad 1, I know the side opposite will be 2 and the hypotenuse will be 3 because the sine was 2/3. So using Pythagorean theorem, I can figure that this would be, let's see, 3 squared equals 2 squared plus x squared. 9 minus 4 would be 5. So x will be the square root of 5. So I can figure out that cosine of alpha will be rad 5 over 3. And I will use that here in this part of the identity. And then I also can figure out sine of alpha. Sine of alpha is 2/3. Opposite over hypotenuse. Okay. Then I draw a different triangle for beta. This one is in quad 4. And I know that cosine of beta is, over here. Tan of beta is negative 3 over 4. So I know the opposite side is negative 3. The adjacent side is 4, making the hypotenuse 5. So then cosine of beta would equal 4/5. Sine of beta would equal negative 3/5. So now I have all the pieces that I need to be able to solve this identity. And so again, the identity is cosine of alpha plus beta equals cosine alpha cosine beta minus sine alpha sine beta. And alpha, just as a reminder, was equal to the inverse sine of 2/3. That's how I drew this triangle. Beta was equal to the inverse tan of negative 3/4, and that's how I drew this triangle. Okay, so then cosine alpha we know is rad 5/3. Cosine beta we know is 4/5. Sine alpha we know is 2/3. And sine beta is negative 3/5. And then I just multiply, subtract, reduce. So here I get 4 rad 5/15 plus 6/15. So my final answer is 4 rad 5 plus 6 all over 15. And that is my answer to this original complicated expression here. So I could say that, I'll write this way. 4 rad 5 plus 6/15 is equal to the cosine of sine inverse of 2/3 plus tan inverse of negative 3/4. This expression is equivalent to that expression based on the cosine sum identity. Now in example 5, these are the kind of problems that we looked at in 7.4 where you have to establish an identity. That means that this equal sign is not yet established. So you are not allowed to use any properties of equality. Okay, that means we're going to stick to one side of the equation and simplify it and hope that it simplifies to equal the other side. So I notice here again I've got a sum of angles. Here's my alpha and that is my beta. And it's a cosine of the sum of angles. So I'm going to use the cosine identity. So it's cosine alpha cosine beta minus sine alpha sine beta. And I'm going to use pi/2 for alpha and then theta for beta. So I get cosine of pi/2 times cosine theta minus sine of pi/2 times sine of theta. Now, cosine of pi/2, if you recall, is 0. And 0 times anything is 0. Whereas sine of pi/2 was 1. And so it's 1 times sine theta. So I get, that's minus 0 minus sine theta. And as we know, that is in fact equal to negative sine theta, which was the other side of the equal sign. So I bring it down. I check off my equal sign. I show that it is in fact equal. And my proof is done. Similar process over here, except now it's a difference of angles. 2 pi would be my alpha, and then theta would be my beta. And I'm evaluating tangent of those angles. So I will use a difference identity for tangent. And so really quick, I'll just write that what that was. So tan of alpha minus beta is equal to tan alpha minus tan beta all over 1 plus tan alpha tan beta. So I will use 2 pi in place of alpha and theta in place of beta. Okay, so we're starting this identity. We're going to see if tan 2 pi minus theta does in fact equal negative tan theta. We don't know if it does yet or not, so we can't move anything over the equal sign. No properties of equality allowed. We'll just stick to the side, use this identity and simplify it and hope it equals that. Okay, so then I get on this side, I get tan of 2 pi minus tan of theta all over 1 plus tan 2 pi times tan theta. Tan of 2 pi is 0 because the coordinates at 2 pi are 1, 0, and tangent is y over x. So I have 0 minus tan theta all over 1 plus 0 because 0 times anything is just 0. Maybe I'll write it out. 0 times tan theta. So then 0 times anything is 0. So I get negative tan theta in the numerator over 1 in the denominator. And that is, in fact, equal to the negative tan theta on the other side. So I have successfully proved that identity. In example 6, you have one of these U-type questions again, where you are given a trigonometric expression with trig functions, and you are asked to write an algebraic expression with U and V. So again, these, I think, are the trickiest kinds of problems because you have to recognize what is an angle and what isn't. So, sine inverse of U is an angle. That we'll just call it angle alpha. Cosine inverse of V is also an angle. We'll call it angle beta because they're answers to an inverse trig function, which are always angles. Meanwhile, U is a ratio of two sides, U over 1. V is a ratio of two sides, V over 1. U is a sine ratio, so it's opposite over hypotenuse. V is a cosine ratio, so it's adjacent over hypotenuse. So I can use that information to sketch triangles. So for angle alpha, the opposite side is U and the hypotenuse is 1. But for angle beta, the adjacent side is V and the hypotenuse is 1. So here I would have to figure out the adjacent side for this triangle. So I would use Pythagorean theorem. And I would get that this side is the square root of 1 minus U squared. And then I would use Pythagorean theorem over here and find that this third side is the square root of 1 minus V squared. And then I'm going to use the identity for the sine sum of angles, sine alpha plus beta. Because that's what I have. I have sine of a sum of two unknown angles. Sine inverse of U and cosine inverse of V are angles. So it's sine alpha, cosine beta, plus cosine alpha, sine beta. Sine alpha is U. Cosine beta is V, because it's V over 1. Cosine alpha, it would be this adjacent over hypotenuse, so it's the square root of 1 minus U squared over 1. And then sine beta is opposite over hypotenuse, so it's the square root of 1 minus V squared over 1. So my final answer would be UV plus, and then I can multiply these together inside the same square root because they're both under a square root. So I FOIL them. So I get 1 minus 2U squared V squared plus U to the 4th V to the 4th. That would be my algebraic expression that contains U here and here and here, and V there, there, and there. So this is the trig expression. This is the algebraic expression. You would do a similar thing here. The only difference is that I am finding secant. So I know that secant of a sum of angles would equal 1 divided by cosine of a sum of angles. And again, tan inverse of U is my alpha. Cosine inverse of V is my beta. So I'll make a couple triangles here. So for alpha, U is the ratio of sides because it's inside an inverse trig function, so it's a ratio of sides. It's U over 1. V is a ratio of sides, V over 1. U is a tangent ratio, so it's opposite over adjacent. V is a cosine ratio, so it's adjacent over hypotenuse. So for alpha, I'm given the opposite and adjacent sides. So the opposite side is U, the adjacent side is 1. For beta, I'm given the adjacent and hypotenuse. So the adjacent side is V, hypotenuse is 1. So I can use Pythagorean theorem to find the missing sides. So in this case, the hypotenuse would be the square root of U squared plus 1. In this case, the other side would be, the opposite side would be the square root of 1 minus V squared. And then I'm just going to do the reciprocal. So actually, first what I will do is find cosine of alpha plus beta and then take its reciprocal. So cosine alpha plus beta is cosine alpha cosine beta minus sine alpha sine beta. So cosine of alpha, so here's my alpha triangle, cosine is adjacent over hypotenuse, would be 1 over the square root of U squared plus 1. Cosine of beta would be V over 1, so that's V. Sine alpha would be U over the square root of U squared plus 1. Sine beta would be the square root of 1 minus V squared over 1. So then I get V over the square root of U squared plus 1 minus U times the square root of 1 minus V squared all over the square root of U squared plus 1. Let's continue this one onto the back. So then I get V minus U times the square root of 1 minus V squared all over the common denominator of the square root of U squared plus 1. Okay, so that right there is cosine alpha plus beta. But what I need to find is secant alpha plus beta. And that is just the reciprocal. So I just take this fraction and flip it over. So it will become the square root of U squared plus 1 all over V minus U times the square root of 1 minus V squared. That is our final answer. That is the algebraic expression containing U and V that gives the same value as this trig expression given secant and then alpha and beta.